Derivatives of exponential and logarithmic functions. To begin with, we have a theorem, the derivative of exponential function. If f of x equals e to the x, then f prime, the derivative of f, equals e to the x as well. It's worth noting that the exponential function is the only non-trivial function that is its own derivative. Just kind of a neat fact. Now, in general, the chain rule applies. If f of x is e to the g of x, you have a composed function, then f prime is e to the g of x times g prime of x. So let's dive into example 1. Find the derivative of f of x equals e to the 3x. Well, that means we have e to the g of x, from that right there. So we have e to the 3x times the derivative of our g of x, which in this case is 3. So let's go ahead and write that as 3e to the 3x. Example 2, find the derivative of f of x equals e to the tangent of 2x. Now we actually have two compositions of functions here, so we'll use our chain rule twice. So first, this will be e to the tangent of 2x times the derivative of tangent of 2x. Well, that is secant squared of 2x times the derivative of 2x, which is 2. So written better, 2 secant squared 2x e to the tangent of 2x. Alright, check out the OpenStax Calculus 1 volume at that web address right there. It's a great book. Example 3, the derivative of e to the x squared over x. Alright, well, let's go ahead and mark these up as our u and v. So low d high for the derivative here. So low d high, so that would be e to the x squared times the derivative of x squared, which is 2x. Low d high minus high d low, that will be times 1 over low low, so x squared. Now we can factor out the e to the x squared, which leaves us with 2x squared minus 1, and that is all over x squared. Number 4. A colony of mosquitoes has an initial population of 1,000. After t days, the population is given by a of t equals 1,000 e to the 0.3 t. Show that the ratio of the rate of change of the population, a prime of t, to its population, a of t, is constant. So in the end, what we actually want to show is that a prime of t divided by a of t is some constant. Well, let's first figure out a prime of t. So let's go ahead and this is what we want to show. So a prime of t over a of t. The derivative there would be 1,000 e to the 0.3 t times 0.3. Right, so that would be 300 e to the 0.3 t divided by 1,000 e to the 0.3 t, which is 3/10, 0.3. So, is that in fact a constant? Yes. Yes, it is. Okay. Let's move on to number 5. The derivative of x times e to the 2x. So let's mark this up as our u and our v function. So for our derivative, we have the derivative of the first, which is 1 times the second, e to the 2x, plus the derivative of the second, which is 2e to the 2x times x. Let's go ahead and factor this. Let's take an e to the 2x out of both terms. So we have 1 plus 2x. And that is our derivative in its simplest form. Next we have the definition or the theorem for the derivative of a natural logarithm function. So if x is greater than 0 and y equals natural log of x, and naturally, no pun intended, the domain of the natural log function is x being greater than 0, then dy dx is 1 over x. Now, more generally speaking, we can apply the chain rule to this, and we'd take the derivative of that. So this would be, and commonly this is written as y prime equals 1 over g of x, 1 over g of x times g prime of x. If you're thinking the chain rule, take the derivative, multiply by it, of the inside function. So I generally write that as the derivative of the inside function divided by the function itself. Means the same thing, but it's another way to write it. So with 6, find the derivative of this function. This is f prime of x equals the derivative of our inside function. That will be 3x squared plus 3 divided by the inside function. So x cubed plus 3x minus 4. It might be a good idea to factor that. 3x squared plus 1 over x cubed plus 3x minus 4. Ooh. Let's make that a little bit better. Now, because x squared plus 1 is a sum of cubes, it does not factor over the real numbers, so we can just leave that as our derivative right there. All right, number 7. Find the derivative of natural log of x squared sine x over 2x plus 1. Now, to begin with, you are probably thinking we've got the product rule, the quotient rule, and natural logarithms. That's true. We do have all of this in one problem. However, if we use our log properties to write this as the natural log of x squared plus the natural log of sine x, I'm going to go ahead and put this in parentheses. Yeah, we'll do that. Minus the natural log of 2x plus 1. If we write it with our log properties in that way, this is a whole lot easier. So the derivative of each term there would be, in this case, 2x over x squared plus cosine x over sine x minus 2 over 2x plus 1. Now that can simplify just a bit, and we can make this 2 divided by x plus cotangent x minus 2 over 2x plus 1. And there we have our derivative. So logarithmic properties can come in handy. For instance, with this question right here, we can write this as 5 natural log of 3x plus 2. So calculating our derivative, we can leave the 5 alone. It's a constant. So 5 times, and the derivative of 3x plus 2 is 3 over 3x plus 2, making our derivative 15 over 3x plus 2. Okay. Now, the general logarithmic function, meaning we have a log base b, rather than a log base e, which is what the natural log is, the only difference is what I like to think of as a scaling factor, which is we have in our denominator we have the natural log of b. Go ahead and underline it right there. All right, so the same property applies, we just have this divided by natural log of b. Now, the general exponential function, that's b to the y equals b to the x, we multiply by a factor of that base there as well. Okay. So let's go ahead and try one of these. The derivative of 3 to the x divided by 3 to the x plus 2. All right. Well, this is a quotient rule, so uv. So low d high, 3 to the x plus 2. The derivative of the numerator there is 3 to the x times natural log of 3. Minus high d low, so 3 to the x, and the derivative of the denominator is natural log of 3 times 3 to the x, or I suppose writing it the same way I did the last one, 3 to the x times natural log of 3, all divided by low, so 3 to the x plus 2 squared. Alright, so we can take the 3 to the x, we'll factor out the 3 to the x times natural log of 3, which leaves a 3 to the x plus 2 minus 3 to the x. Alright, 3 to the x plus 2 squared. And f prime of x is 2. I'm going to go ahead and rearrange this. 2 natural log 3 times 3 to the x over 3 to the x plus 2 squared. And there is our derivative. Number 10, find the slope of the tangent line, or the line tangent to y equals log base 2 of 3x plus 1 at x equals 1. Okay, so first we will find our derivative. Really what we're after is dy dx evaluated at x equals 1. All right, so the derivative of that function, in general, we have the derivative of the inside the composite function, so 3 over 3x plus 1 times natural log of 2. I'll just go ahead and write it that way. So we want to evaluate that at x equals 1, which would be 3 over 4 natural log 2. Well, that's the slope. So that is the slope of our tangent line. Number 11, find the slope of the line tangent to y equals 3 to the x at x equals 2. Same idea. Our slope is dy dx evaluated at x equals 2. And the derivative of that is natural log 3 times 3 to the x, or I'll keep writing it the other way. 3 to the x natural log 3. So evaluating that at 2, that is 9 natural log of 3. That is the slope of our tangent line. All right, number 12. We now come to something called logarithmic differentiation. This is a really useful tactic if we have functions as exponents, because we can't use our power rule when we have a variable as our exponent, or whenever it'd be helpful for products to be sums, quotients to be differences, etc. So let's go ahead and work with this one. Y equals 2x to the 4th plus 1 to the tangent x. Well, we need to get that tangent x, that function, out of our exponent. So what we do first is we take the natural log of both sides. So the natural log of 2x to the 4th plus 1 to the tangent x. Now, we can use log properties from here. We'll bring the tangent x down, natural log of 2x to the 4th plus 1, and we have natural log of y. All right, bringing that out, we can now use the quotient rule. We'll take the derivative of both sides. So on the left side, this is going to be, we'll use implicit differentiation. This will be 1 over y times dy dx. Now we have a product here, uv. So the derivative of the first is secant squared x times natural log 2x to the 4th plus 1 plus v prime, which would be 8x cubed over 2x to the 4th plus 1. times our tangent. Now, the last step we want dy dx, so we are going to multiply both sides of this equation by y. Multiply both sides of this equation by y. Now, if you recall, y is actually 2x to the fourth plus 1 to the tangent x. So we get dy dx equals 2x to the fourth plus 1 to the tangent x times secant squared x natural log of 2x to the fourth plus 1. Oh, don't need that parenthesis there. Plus 8x cubed over 2x to the fourth plus 1 times tangent x. So that whole quantity multiplied by our original expression. Now, obviously, that is a very complicated derivative. So there are other methods we can use, however, this is the best. So if you recognize where log properties would be very helpful, moving exponents down, or splitting products into sums, quotients and differences, etc., recognize that and take the natural log and see what happens. All right, number 13, find the derivative of y equals x square root of 2x plus 1 divided by e to the x sine cubed x. Alright, this is crazy by itself. Now, if we take the natural log, here it'd be nice to make the radical into an exponent, which we can bring down with log properties, etc. So this becomes natural log of x. I'm going to go ahead and write this as an exponent over e to the x sine x cubed. So this is going to be natural log of y, and I'm not, actually let's bring this down. I'm not taking my derivative yet. Keep that in mind. This is the natural log of x plus 1/2 natural log of 2x plus 1 minus natural log of e to the x. Now all of this is in the denominator, so we will subtract all of it. Natural log of, actually that would be 3 natural log of sine x. So let's go ahead and distribute that and make that a negative term there. Now, taking the derivative of each of these pieces here works out very nicely. This is 1 over x. 1/2 times 2 over 2x plus 1 minus 1, because the natural log of e to the x is just x, minus 3 cosine x over sine x. Now, multiplying through by our y, this becomes dy dx is 1 over x plus 1 over 2x plus 1 minus 1 minus 3 cotangent x, cleaning that up just a little bit, times x square root of 2x plus 1 over e to the x sine cubed x. And there we have our derivative. All right, last example for this section is a classic problem. This one comes up a whole lot as just the perfect example of logarithmic differentiation. First, we'll take the natural log of both sides. So we will have the natural log of y equals x natural log of x. Taking the derivative, we have 1 over y dy dx. And this is a product rule. So we have uv. The derivative of the first is 1, so 1 natural log x plus 1 over x times x. So natural log x plus 1. is 1 over y dy dx, multiplying through by y. This is dy dx is x to the x natural log x plus 1. And there's our derivative. All right, now that brings us to the end of this section. So again, I'll point out that interesting fact that the exponential, the natural exponential function, is the only function that's non-trivial that is its own derivative. Just an interesting fact. But logarithmic properties turn out to be very handy sometimes, so keep this kind of in your tool belt, keep it in your back pocket. That's the end of section 3.9.